Okay, so yes. So you guys may have went over the multi-layer perceptron, the MLP. So the problem, there are some problem with the fully connected layer, especially when processing image data, which motivated the convolutional neural network. Does anybody recall this from the previous lecture? Anybody want to take a try? Mm, right. So actually this we will cover in the later lecture, but because in the fully connected layers, we are connecting like say if there are 9 input neurons and 4 output neurons in the output layer, then since they are fully connected, there will be in total 36 weights. So 36 outgoing edges from in total from the input layer to the output layer. So there are many parameters which usually this could lead to overfitting because as the learning capacity is high, um, there could when the task is simpler than its the learning capacity required, then the model could start memorizing the training data instead of learning general patterns, which that makes it prone to overfitting. And also, the when you process image data with the fully connected layer, you are not considering the spatial structure because if we have an image data of say four by the height 4 by 4 pixel, then we are squashing into a one dimensional vector, and then we are learning from it. So that also is no longer considering the spatial structure which motivated the convolutional neural network approach, which considers the spatial structure by using filters. So any questions on this part? Okay. So this slide is showing the in the left diagram is showing the fully connected the MLP, the multi-layer perceptron, and the right diagram is showing the convolutional neural network. So as I've just explained, we can see that the input layer, despite this might be an image input, the input layer is one-dimensional, which means that the spatial structure is being flattened into a one-dimensional input layer, whereas in the right diagram, we can see that the input is currently a cube, but it takes care of the width and the height, which we can understand that as the image's width and height. So now the next question would be, why is there the third depth of the input, the red cube? So anyone recall what that is? What the depth of the red cube, the input cube, of course, can see that after the next layer in the CNN, we can see that the blue cube is low, is more condensed, more but deeper in depth. So this indicates that the in the first layer, the CNN tries to learn more of the local regions of, and then based on the understanding of the local regions, it expands to. So when you try to understand the object, you would want to first understand the local regions separately, and then try to aggregate that information to get a more broader understanding. For example, if you want to understand, recognize a cat, you may want to first know how to um, detect the edges, the shape of the cats or the boundaries of that cat figure. And then once you gain that kind of understanding, you could understand, oh, this is the head of the cat, which which expands to the recognizing the entire cat in the end. So that explains why the width and the height of the second cube it gets smaller, and the expanded depth means that you understand um, more sophisticated features from the image, starting from the RGB, which in the end, typically these, once you gain enough understanding, it in the rightmost of the second diagram, the right diagram, we can see that the the features are condensed to a 1D vector, which this typically could be used for the machine downstream task of machine learning, such as a classification or other sorts of for other task use cases. Okay, so the principle of the CNN is the first one, which you guys may have already went over. Is the first one is the translation invariance. So, in the higher level, translation is basically the object moving within, appearing in different locations within the image. So if you have if there's a cat in the image, regardless of where it appears, you would want to be able to detect it. And the locality principle is that the second principle is that the earliest layers, this is which corresponds to the example that I've explained in the previous slide, where in the earlier layers of the CNN, you would want to focus on the local regions, such as detecting the edges or the, the the local patterns. Then you would want to um, progressively gain the understanding to get the more global understanding of detecting the cat itself, starting from the cat's regional features. So these are the two principles for CNN. And please let me know if you have any questions or doubts, which I would love to address. Um, so the convolution of the images itself is basically there's a kernel in the middle of the diagram, which each of the values in here are learnable weights, the parameters. So during the training of the CNN, based on the supervision signal from the loss function in the end, these values in the kernel will be updated through the backpropagation. And these kernels could have some, these are learned during the training, but these kernels could be understood as, for example, in this 2 by 2 matrix, this kernel, if the second column is all 1 and the left column is all 0, that would be the first column being 0, 0, and the second column being 1, 1. Then this could emphasize the right in an image. If you want to emphasize the right edge, then that kernel would achieve that, because the 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 input in the input 3 by 3 matrix, it would emphasize the the second column because it's all 1, whereas the left column is all 0. Um, and each kernel will basically, you guys must have already learned, but it's will compute, will pass through the input where they are the same, with the uh, we'll compute the dot product with the corresponding input patch within the input matrix. So as you can see, the dot product of the blue region in the input matrix and the kernel will be 19. And and this will decrease the dimension when it comes to the output matrix. As you can see, the input matrix was a 3 by 3 matrix, but after going through the 2 by 2 matrix of kernel, the output matrix reduces to 2 by 2, where the formula that computes the output matrices dimension is shown in the maybe I could have a red laser. Is my spotlight visible? Yep. Yep. So the input matrix, the dimension, this square matrix is n subscript h, which is 3, minus kernel's dimension is 3 minus 2 plus 1 is 2. So it's a 2 by 2 matrix in the output matrix. So the dimension got smaller. But if the dimension gets smaller and smaller by applying such kernel, then when we try to make the CNN deep, then if it only gets smaller, then it would be a problem because we will no longer be left with an output matrix which could serve as the input matrix for the next layer. So for this, the concept of padding was introduced, which includes the 0 pads in the edges of the input matrix. So the input matrix in this image, we can see that as a 3 by 3 matrix. Now, after padding, it became a 5 by 5 matrix, which the edges are all 0. So by applying this, we can see that the output size is no longer 2 by 2, but actually 4 by 4, which increased from the input which was originally 3 by 3. And this also has an effect of letting the kernel attend to the edges of the original input matrix, meaning without padding, the kernel would be computed to would be applied to the input matrix in the first time as the top left submatrix, 2 by 2 matrix, which is 0, 1, 3, 4. But when we apply the padding, it can be applied to the some input submatrices of the blue region 0 by 0, 0, 0, 0, 0, and also the next one of 0, 0, 0, 1. So this indicates that the kernel can also produce values based on the edges. So we can detect patterns from the edges of the image. So this is another, the two advantages. It can now attend to the edges of the image, and also it can preserve or even increase the dimension of the output which output matrix, which facilitates more deeper layers of the CNN. And this is again the formula here is the dimension of the resulting matrix, which the NH was 3, as we know, and the kernel was 2, and the pH here is 2 because we are applying in 2 directions, which is 3 minus 2 plus 2 is 4. So the resulting matrix is a 4 by 4 matrix. And so another concept here is stride. So in the previous examples, so when the kernel slides through the first horizontally slides through the input matrix until it hits the end, and then goes down, and then that restarts in starting from the next row, the but so the striding itself happened as one step at a time. But this stride concept will enable the kernel to step at two steps at a time, which to clarify, starting from the top left sub 2 by 2 submatrix, it slides two steps to the current blue submatrix, which is 0012, and skipping the intermediate submatrix 0001. So this this would lead to less dot product computation because we're skipping one computation, which would naturally lead to a smaller smaller sized output matrix. So striding is one way to decrease the dimension of the output matrix, which uh, in formal terms could be used as the downsampling. So another downsampling method, which you guys may have went over, is a pooling, max pooling or average pooling. But striding is an alternative for downsampling along with the pooling. And while also considering the 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 spatial structure, but in a more sparser way. And the formula for computing the output of the stride is given as in below. Yep. Okay, so for this for this multiple input channel, so this indicates that we only talked about the previous example only covered the the single channel cases, but now we can see that the input matrices are overlapped. So we have multiple channels here, and we also have two separate kernels here, which are each of them are being producing a dot product in the multiple channel and point of view. So as you can see, the input matrix that's in the front is being applied with. So this slide could be a little bit misleading for some people. So so there is a equal sign in the over here, so you can more focus on the right part of the of this image. So for each channel, it will generate the dot product, and then that dot product will be added to the dot product of its counterpart in the other input channel, which will result in the output matrix. So this is basically aggregating in terms of multiple channels into one. And any questions? Okay.
So,
Yep.
um, since the kernel is being used for each input, um,
Yes, you have two separate kernels for each channel, input channel.
right?
Yes.
Um, is that what comprises the filter? The
Right. So, right. So here there could be yes, that's correct. So usually it's actually in the next slide, but yes, one filter can include multiple channels, which your understanding is correct. That's what you're saying. right?
Right. Yeah.
Yes, because sometimes people can use a kernel and filter interchangeably. So, but yes, the you can understand formally as one filter including multiple kernels. Yeah.
Right. So
Okay.
for the next output, like
Mm,
the 72, right?
yes.
Um, would you just would the stride be one and the values that are taken would be the one, two, four, and five out of the
Mm, right. You're talking about the 72, right? In the
yeah.
yes, that will be computed by applying the in the above pair, the input kernel pair, you will apply the kernel to um the sum matrix of the input matrix of 2356, this part
Right.
applied by
And
kernel, and then you get a
one, two,
dot
four, and
product.
five.
Yes. Yes, 1356 sum matrix, input sum matrix will be applied with the kernel of the 1234 one. This one. Is my red pointer visible in to
Yeah,
you?
yeah, it is.
Yes, right. And the counterpart will also be computed, which would be added to get the scalar the out in the output 72.
Okay. And
Yes.
for the stride, is there a stride
Mm.
going horizontal and vertical?
Yes, that's correct. Yes.
Okay.
So it's skipping horizontally and vertically. Yes, and you can set the stride as different numbers. Yeah, more than two. Yeah. Is that clear?
Yeah, thank you.
Okay. Yeah. Thank you. Okay. So yeah, maybe the uh yeah the Jimson, yeah, Jimson made a good point that so here we are seeing in the input we have three input channels here, as you can see, and have two filters with each filter including three kernels, and the output is, we can see that there's two channels. So Jimson, what would you like to take a try on why the output would be two channels?
Is it because there's two filters?
Exactly, yes. So the output channels number of channels will correspond to the number of filters applied. Yes, so each filter will be trying to learn some kind of feature from the input. So we can think of it as like this. We already have went over that the input could be RGB, such as the red, blue, gray, red, RGB, yeah, red, green, blue. So if each channel correspond to RGB, then and each pixel is the grayscale of within that each of the RGB. Then we want to learn a particular feature which correspond to each kernel, and that will be applied to each of the three dimensions of the input, which will be aggregated into one understanding of that feature from the three channels of the input, which in this diagram we have two of such um, kernels or feature detectors. So we're getting two output matrices. Yep.
So one quick
Okay.
question
Yeah.
about the
Okay.
previous slide.
Yes.
So are the kernels all the same for that one input?
All the same, meaning meaning the
Like
numerical values.
for the one filter,
Hmm.
um, is the value of the kernel going to be the same for the input?
No, that corresponds to this slide. Um, so that's your question, right? Whether in the kernel, if they correspond to the same filter, will the kernel be duplicate to each other or not? That's your question, right?
Oh, okay. So the filter has different
Hmm.
kernels, and these kernels have different values attached to it.
Yes, which
Okay.
will be learned out. Yeah, that's right.
Okay.
Yep. I think someone. Yes. Thomas posted a question. That's right. I Yes, that's correct. The slide is two, and the reason for that is um because of the location of this matrix here. Because we already know that the stride slide is not assuming that the stride is one, but something greater than one, and so the blue submatrix here will be the next one. Uh, Yep. Division is 2.5. I did not understand the question. Division is 2.5. I think you're referring to the formula, right? I see. Okay, so for this formula, the NH is 3 and the AH is 2 and the pH is also 2. And then, right, but it's the lower. I mean, after 2.5, I think, getting the lower value in the end. It's a 2.5 becomes 2. So I think my understanding of your question, yes, I think, and one other student has come in. Okay, one more student joined. For the student who joined, could you please write? I'll take care of it. Yeah. Okay, so we can go over the maximum pooling and average pooling. So yes, so I've also mentioned earlier that this pooling is also one way to uh, perform the downsampling, which is basically reducing the dimension of as you can see here from the input to the output. So so as a caveat, there's the maximum pooling and the average pooling. Here it's basically again going through each submatrix of if you're applying the 2 by 2 max pooling, we are for each 2 by 2 submatrix of the input matrix, we're extracting the max for each of them, and then that will be the new value in the output matrix. And for similarly for the average pooling, we will be computing the average. So and in terms of if we think it in more high level, the max pooling. Anyone have some understanding what kind of effect the max pooling and the average pooling might result in. If you think of as in an image, maybe my question was not too clear. So the max pooling typically tries to make the characteristic of that image more what should I say? Okay, the average pooling might more smoothen out the image, whereas the max pooling would make the features more clear. So that would be one intuitive understanding that you can think about for the max pooling and the average pooling, and also uh, another aspect from that is that when you usually apply deep learning or convolutional neural network, you want to learn some nonlinear patterns. Um, Instead of just linear patterns. I'm not saying that this max pooling itself is defined as nonlinear, adding nonlinearity linearity to the model, but we can think of it as the max pooling as introducing some aspect of nonlinearity to the model because we're not scaling or shifting from the input to the output. We're just picking the highest one. So that's another aspect to we can think about. Um, okay. Okay. So the LeNet is one of the most earliest CNN architecture. Okay. Which so first of all, in this image we can see that it's not a cube. It's just let's see. It's an 8 by 8 matrix, 28 by 28 pixel matrix. And we can see that this image resembles the digit of 7. So what this CNN is trying to do is trying to apply this convolution and pooling and all the concept we have learned to this image. And then the end goal is to try to classify which image will be mapped to which digit, which we can see in the output. The end is the 10-dimensional. So this may have applied a softmax activation, which for each digit might result in some probability whether this image corresponds to 7 or 6 or other digits. So this is a rather shallow architecture since it was the first one. And as we have seen, the feature map in the first C1 feature map, the dimension of the image, the width and the height is preserved, but it's learning different features and it gradually decreases. So the width and the height are decreasing from 28 by 28 to 14 by 14, 10 by 10, 5 by 5, but the dimension, the channel is increasing, learning meaning that it's learning more sophisticated features, which will later, after applied with pooling, will be flattened and applied with MLP, the fully connected layer, to learn for the downstream task itself, and then it will output some softmax vector, which which will be applied to compared with some loss function and will be used to update all the weights, not only in this MLP but um, also the weights that's learned in between the convolutions. It, yes, so this is the LearnNet 5 block, which is basically represent block representation of this image. So right. So for this uh part, yes, I'm pretty sure that you guys may have learned the concept of the block and layers. So it's just a modularized representation. So we can see that the in the beginning it's being applied with a 5 by 5 convolutional layer with a padding of 2, and then so all the concepts that we learned are being applied here. So the takeaway is just that this is a block representation of the Linnet. Okay, and yes, so the CNN is a network that employs the convolutional layers, and which interleaves the convolutions and nonlinearities and poolings. So anyone have some could try to explain why the network having nonlinearity is important. And in this CNN, where we learned where the nonlinearities are being applied, would anyone want to take a chance?
What was the question?
Right. So in the CNN, where the nonlinearity is coming from? Right, because the non we want to learn model to learn some nonlinear patterns, right? Relationship between the input and the output instead of just learning some linear patterns, which is shifting and scaling. So from the CNN that we learned, where would the nonlinearity be coming from? Yeah.
I mean, isn't it from like using
Mm.
activation functions?
Yes, exactly. So where would the activation functions be included in this diagram?
Would it be like the convolutions,
Exactly. And also,
the pooling?
um, no, the pooling doesn't involve uh, activation, but it would be in the dense layers here, the MLP. Yeah,
All right.
yeah. Okay, and that's a good answer. Okay. Um. Right. So as we discussed, as we mentioned, the convolutional layers are arranged so that they can decrease the spatial resolution, meaning that the width and the heights are being decreased as we progress through the convolutional layers. And but the number of channels increase, which the depth is increasing in terms of the cubical representation, so that we're learning more complex patterns. So
Quick
and
question.
also yes,
So you said in the dense layers like allow non-linearity.
yes.
Um, what do they do in the like what happens in the dense layers with the um with the
Mm.
smaller input dimensions?
Like in 84, right? The smaller
Yeah.
one. Right. It's basically just applying an MLP to learn a typical MLP to learn patterns. Yeah.
Okay.
Yeah. Right. So
So
basically, mm,
each of the dense ones are um a layer or like a layer in a MLP.
yes. So basically, we're overall we're having two tasks, such as the first task would be more of the understanding of the image, starting from this part, the part which includes convolution or pooling, and then the dense layer. This is more dedicated to for the downstream task of classification, but also the weights of this first step, convolution and pooling, are being updated in order to succeed with the task of classifying with the correct digit. Yeah, but um, yeah,
So is the dense layer where the gradient of the weight and the input is coming from?
it the all the supervision signal will be coming from the loss function in the end. Yes, so it
Okay,
will back propagate. Yeah,
right.
yes, right. Okay, okay. So right, right. As we just discussed, so in the traditional CNN, after the convolutional blocks include the representation, one or two more MLP. The fully connected layers will be added, stacked to the end so that we could produce the output. And this one was the first um, model.
So what would the output be? Would that also just be a um like after the dense layers? What is the output?
Mm.
Is it also like a image with smaller dimensions?
No, no. The output here after the dense layer would be the downstream task output, which in this case, the task is multi-class labeling, which we want to classify an input, which includes some digit. Here is 7, right? We want to classify some number between 0 and 9.
Okay.
So yes, so it would be the probability. Yeah.
Oh, so it's the probability of the image being from 0 to 9.
Yes.
Okay.
Yes, each. Yes, yes,
Okay, got you.
yes. The representation would more correspond to the here 1655, the S4. Yes, which you were interested in. Okay. Okay. So the advantage of a CNN, which I have also uh talked about in the beginning, is that it involves a less number of parameters. So the MLP could be over parameterized if there are 9 input neurons and 4 output neurons. Then since they are fully connected, it would result in 36 parameters to train. And also they are flattened into a one-dimensional vector, so they do not consider a spatial structure, which means that the the model will be have a difficult time to identify the same object in the image being rotated or appearing in a different location and so on. The translation invariance. And but the CNN, first of all, uses this fixed kernel, which are learnable weights, but much smaller in number. In this 2 by 2 matrix of the kernel, there are 4 parameters to train, opposed to 36, and also takes into account the spatial structure, so it's more robust to detecting the rotation or other variations in the input. So these are the main advantage of the CNN. Um, And also the AlexNet here is one of the the more advanced version of the CNN, which the takeaway from this is that it replaced the sigmoid activation function to a more simpler ReLU activation function, which sigmoid, I'm supposing that the students may have been learned of the vanishing gradient problem, which the sigmoid activation function could introduce as the model gets deeper. So by using a ReLU activation function, they were able to construct a deeper architecture. As you can see in the diagram, we can see the left one corresponds to the LeNet, the earliest version of CNN, and the right diagram, this one corresponds to the AlexNet, which is deeper than the LeNet. And it has 10 times more convolutional channels, which allows it to learn more complex patterns. Yes, so for this slide, the takeaway is that this VGG block is that they are reusing the same block, the VGG block, in, as you can see in this part of the diagram, they're reusing the same block in different places, which has advantage in terms of the implementation and the maintenance. So that would be the main takeaway from this slide. So they modularized the CNN. Right, maybe it's 5 minutes. One more student came in. Okay, so I will quickly go over the evolution of the deep learning. So the deep learning itself was not the mainstream because of not a lot of data as of now was available, and also the computational resources where right now the GPU enables parallelism in the matrix multiplication, which leads to very efficient computation. And a long time ago, that was not available. So the neural networks were conceptually there, but other more theoretically elegant machine learning methods, um, such as support vector machines, or more mainstream. And also some key tricks in updating the weights of the neural network were not there. So that would, which some of them will be go over during the deep learning part of this lecture, which was later developed, which enabled the deep learning becoming more mainstream. Yes, so this basically reiterating what I said, that the deep models with many layers require large amounts of data, which was not available back then. And the hardware, the GPU, involving parallel matrix multiplication, also was a game changer for the deep learning. And also from the deep learning training also lacks some small tricks in terms of the learning rate or also the optimizer. Also, the model architecture improved, which led to the deep learning becoming more mainstream. So the key components for designing the deep neural network are, we would want to first come up with the architecture itself, such as number of parameters and the connections between the layers and the neurons. And also there's a challenge in the optimization, such as which loss function to use for which task, such as in the earlier example of the LeNet, since we had a multi-class classification problem, multi-label classification problem, we would want to select the soft. One way would be to select the softmax loss function, whereas for other tasks, we would want to select other kinds of loss functions. Oh, sorry. The loss function that we want to use in that case, the softmax is an activation function, and the loss function that we would want to select for that task would be a cross entropy loss function instead of softmax. And also, we would want to come up with a learning rate. So when we update the weights of the model um, to the direction where the gradient descent is the gradient is steepest, we'd want to also select the step size, how much we would want to, the degree we would want to update the weights. That would be the learning rate. And also we would want to the optimizer is the approach, how the technique in we how we will update the weights, such as will we compute the gradients based on one sample or the full training data or some subset of it, so that would correspond to that part. I believe from 3:45 to 4, it's so for the students who joined late, I believe there are some of the students who joined late. Could you please um in the chat, could you please write something so that I can use for attendance later? I think I did remember some. Okay. Okay, so yeah, I will resume the course. Okay, so one of the architectural advances for the after the AlexNet, which inherited the LeNet in terms of the CNN, was GoogleNet. So this is one example where the architectural advancements led to uh, the greater performance. And in this case, the takeaway from this slide is that you can see in the we can see that there's some layers that look different from other convolutionals. So these are introduced the parallel convolutional paths. So these are each of these blocks include parallel convolutional paths, which we'll go over the next slide. So this is one architectural advancement. And you can see that these are very deep by being this one being stacked by 2 and the next one being stacked by 5 of these blocks and so on. Another takeaway is that they have, instead of having the fully connected layer MLP, instead of having multiple stacks of that in the end, they applied the global average pool, which for each resulting channel feature map, they extracted a scalar value, the average value from each channel, directly converting into a vector instead of going through the multiple layers, which this also was able to decrease the number of parameters needed for training, so reduce the overfitting, and is which that resulting vector was then applied to the more simpler fully connected layer for the classification. So these are the examples where the advancement of the architecture led to better performance. So we can see that this first of all, this is called the inception block because they are learning in the movie Inception. They're basically going deeper in terms of someone's subconscious. So their intention was to make this architecture a very deep CNN. as you can see by the number of stacked layers blocks, but also they introduced one of the contribution for this architecture was that they introduced the parallel convolutional paths instead of stacking them linearly. So you can see that for each input, they are capturing visual patterns at multiple scales, such as using the 3 by 3 convolutional layer, and 1 by 1 convolutional layer is preserving the spatial resolution, but it's mixing the information across the 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 input channels, so aggregating them into one. And also another scale would be 5 by 5, and then later they concatenate the outputs. And here concatenate is being done depthwise, such as stacking by depthwise, which they will pass to the next layer. Another architectural advancement in the deep learning is the residual block, which some of you may have heard of the ResNet, which in the left diagram, the left diagram shows the um the the normal block, which is basically the right diagram corresponds to the residual block, and the left diagram is not the residual block. In the left diagram, we can see as normal, we are inputting x, which going through the same weighted sum, and then goes through the activation function in order to learn some function of f of x. Whereas in the right diagram, the input is the same component of the weight layer, the same block, is not trying to learn the f of x, but instead trying to learn f of x minus x. Whereas the input is directly being passed through a connection, which this is a skip connection or residual connection, and then they are aggregated afterwards. So this can be understood as the function itself, the weight layer itself, is trying to learn the incremental change or the correction from the x while just passing the x directly, which first of all, first advantage of this is typically the task of trying to learn the connection is an easier task for the neural network um, compared to trying to reconstruct the X itself throughout the whole network. And the second advantage is in terms of the vanishing gradient problem, because we know that as the neural network depth gets deeper and deeper, there will be cases where if the activation function, the logit produced by the weighted sum, if the weighted sum is too extreme, too high, or too low for the sigmoid function, we know that such extreme values could result in the saturation region of that activation function, leading to vanishing gradient problems. And this risk gets higher and higher as the neural network gets deeper and deeper. So this means that even though the learning happened well in the later layers of the neural network, if some layer results in such very small gradients or zero gradients, the earlier layers will no longer be able to get past those gradients to update its own weights. So, and that problem is what this residual block is trying to solve, because here, even though the block, the block that tries to learn f of x minus x, which tries to learn the correction, determines that there's no longer anything to learn and results in a gradient of 0. The later layers gradients, the incoming gradients can still be passed through the earlier layers through this skip connection, because when you try to update the weights, the gradients, for each layer, we want to compute the gradient with respect to the input in order to pass through to update the earlier layers, and with respect to the weight itself to update that current layer's weights. But even though that current layer's weights gradients become very small, we can still pass the incoming gradients through this skip connection to the earlier layers, as this partial of f of x to x is 1. So through the chain rule, the incoming gradients will be still passed through the earlier layers. So any questions on this part or clarification? If- okay. So this ResNet, this skip connection concept itself was a very big deal, and also some of you may have also are interested in the transformer architecture, so which led to the current like ChatGPT or the LLMs. So this concept, the skip connection, is also used in the transformer architecture. So this implies that the impact of this architectural advancement was uh, very impactful. So this is the example of the residual block, the implementation of it. Whereas the right one is so it's basically provide the takeaway is providing the residual block being applied in the CNN context, but as I have earlier said, the skip connection can be applied to other types of um, non-image data, non-CNN context. So the takeaway again would be this residual block being implemented in context of the CNN. And the takeaway from this slide would be that since, as I've explained, the skip connection greatly mitigates the vanishing gradient problem, so it enables more deeper networks, because the vanishing gradient problem was mitigated. And this slide shows that there are 3 stacks of uh, this residual block, meaning that this diagram corresponds to a very deep architecture. Okay. Right. Um, so for batch normalization, um, so this batch normalization, is more correct to call it as a standardization than the normalization, because typically normalization is switching the value in between 0 and 1, whereas as we can see in the formulas, we're basically standardizing the values instead of normalizing. And this batch refers to the data sets which we are trying to, the batch of data that we're trying to update the neural network with. So in each of the training iteration, we the basic idea of this, the purpose of standardization or normalization is because when we update the neural network models, we would want to make the training process more stable. Because if the model, the numerical values become too high, then that would naturally lead to, if we multiply high values again and again, then there will be some limit in the upper limit in terms of the data type that could be hold a value, such as a long type, or if the value gets too big in Python, it would be NaN values. So we would want to um, avoid such cases. So that's first of the purpose of trying the normalization. And also we would, the batch normalization, another advantage is that we could avoid, in former terms, the internal covariance shift. If if in, if we have multiple layers and each layer is emitting a very different range of values, then the next layer will try to adjust its weights to process that kind of value. But in each iteration, if that range of values varies too much, then model the layer weights will not, instead of learning something useful, it would try to it would more focus on adjusting itself um to um to process such range of values. So the key insight is that we would want the range of values outputted by each layer into a more predictable range, so that which could lead to more stable and efficient training. So those are the advantage of the batch normalization. And anyone have any question or clarifications on what I've discussed so far? Yeah. Okay. Yes, I will proceed. So for given that we have a batch of data, we're trying to, when we try to normalize or standardize something, we are applying that standardization to based on a set of numbers. So in this case, that set of numbers come from different training samples. So if we're trying to update a neural network based on sample 1 to 10 for a specific um, feature, a neuron, if we visualize one layer, there's multiple neurons, and we want to update uh, we want to standardize the output value which one neuron produces, and we want to standardize it not layer wise, but across the dimension of different samples, which means that for the same input, same neuron for the third, say for example, the third layer, it emits I think some, if it emitted a value of 5 for the first training sample, then that same neuron at the same layer, when it processes another sample, we can expect that same neuron will learn something similar because the samples are somehow homogeneous. So we are for the same training sample, if the output of that neuron is say a 10, and for the third sample is 12, and so on, then we could construct a vector based on those values, and then apply the standardization of computing the mean, which here the sample mean, the beta correspond to the batch. So we're getting the mu hat beta here, the sample mean, and also the sample variance. And then we are trying to standardize each of those output values of each neuron at the same location in terms of the architecture using these values. But we add one epsilon here, which is the noise, because we want to avoid the division by 0. So that part would be correspond to the standardization, but also we um in, there's two more learnable parameters here, which this one is the scaling parameter, and the other one here, which is added, is the shifting parameter, because we want to give the neural network a freedom when we because in some cases, even though we standardize, not performing standardizing could be more beneficial for the the model learning. So we're giving these two learnable parameters so that the model can also learn these two for more optimized training. Um, yes, so also other the batch normalization as I've explained in the previous slide, has those advantages of um, dealing with the internal covariance shift, so leading to more stable training. But also, it has some, I would say, more as a side effect advantage of regularization. And this is because the batch itself, which is used because the batch is the batch of training samples used to compute the standard mean and the sample mean and the sample variance. So that sampling process itself, there's some randomness involved to it. So the sampling of the batch, the sample mean and the sample variance might naturally vary based on the randomness involved with the um, uh, in sampling batch sampling. So that randomness serves as translates into randomness in training, which results in regularization effect. But this part is more of an empirical effect advantage, while not being theoretically exactly characterized. So some associated with this with the try to theoretically explain this, which some of you who are interested in could look into these two papers, where this paper the details are in the I can provide you. Okay. And the batch normalization is, as I have explained, the batch normalization is trying to normalize the output output of the neuron across different samples, the neuron at the same location within the architecture. So, and now the question would be where exactly this batch normalization should be applied. And the paper that introduced this applied this to the pre-activation value, which is the weighted sum added by the bias term. because applying after the activation would not make straightforward sense, because if it was applied with a ReLU function, which which converts all the negative logits, negative pre-activation values into zero, then applying this batch normalization would not it is not a straightforward make sense. And the main reason for applying batch normalization is to keep the active result, is to induce the activation function to avoid the saturation regions in its saturation regions. So naturally, we would want to apply the batch normalization to the logits so that the values are more in a predictable range, with a sample mean of zero and some variations with a zero mean, so that it avoids extreme values leading to bypassing the saturation regions um, and avoiding problems such as vanishing gradient problem. Okay, any questions so far? And so the explanation that I gave you in terms of the applying batch normalization was in context of a normal MLP. So in a normal MLP, each layer has multiple neurons where we can apply batch normalization to the output of the neurons across multiple training samples. But in context of the CNN, the this batch normalization is applied to a channel level. So you can understand as a neuron in context of a layer, a neuron MLP, could be understood as one feature, a hidden feature, a latent a feature. But in context of a CNN, each channel corresponds to a feature. And so batch normalization is being applied at the feature level across multiple training sample within that the random sample batch. So which means that each channel will again have its own scale and shift parameter. I think I forgot to mention this, but this shift and scaling parameter will be recorded for each um, each neuron in context of the MLP. So it adds some more spatial complexity memory, because we're keeping track of these two additional learnable parameters along with the each neuron in the but that added the training stability advantage surpasses the this overhead, spatial overhead. I think some student is if anything is unclear, I I would love to clarify if you let me know.
Yeah, quick question.
Yeah.
Um, you said that did you say that each filter was a feature?
Um. In terms of the CNN,
Yeah, right.
right?
Um,
Each
so
channel, the learned feature, you can understand it. Learned feature, right? The
okay,
filter is basically yeah, yeah. Please go on.
no. Continue. Sorry.
Yeah, no problem. So I was just trying to make a connection, because my explanation was in context of MLP, right?
Right.
So in a MLP, if we have a given a layer, a neuron, right? We can think of it as some learned feature, right? We're learning features across that, right? By its weights.
Right.
This, yeah. Maybe it's a little blurry, but I'm just trying to make a connection. So the counterpart for that neuron in terms of CNN would be a channel, right? The output channel, the matrix, output matrix, because we learned it through the filters, right?
Yeah.
As yes. So the batch normalization is in MLP context is applied to the neuron, which is correspond to the learned feature. So as an analogy, in the CNN context, the counterpart of the um, neuron would be a channel. So we're applying the batch normalization as a channel to the channel as well. So concept in higher level, they are both learned features. So we're doing the same thing, but just in different architecture. Yeah,
Okay.
right. Okay. Okay. Yes, this is um the takeaway from this slide is just that we're adding the batch norm in between and before the sigmoid, as we saw here, we we apply the batch normalization to the the logit, the pre-activation value. So we are applying it before the sigmoid. That's the takeaway. And okay. Okay, so for the right, so in deep learning, most of the objective function or loss function are not do not provide a closed form solution. So we would want to numerically optimize those, which a numerical optimization algorithm we know is the gradient descent. So, but even with that, there are many challenges in this optimization problem, which the tricks that were introduced, which later led to the contributed to the deep learning becoming the mainstream. So some of the known difficulties in optimization is mm, such as vanishing gradients, which we discussed, and also in the loss function landscape, um, because our main goal is to find the global minima, but we may be stuck at most of the time we may converge to some good local minima, but sometimes we would be stuck into suboptimal local minima. And sometimes there'll be flat regions that our optimization being stuck during the training, which one example would be a saddle point. So these are the challenges which the techniques that will be introduced try to overcome. Yeah. Yeah, actually for the vanishing gradients, I think I have explained many times, but we could go over again. So, right. So it, this is an example of the the 10H function loss function. activation function. So we can see that itself um, looks okay, but we know that the activation functions that are bounded, for example, such as sigmoid is bounded by 0 to 1, and tanh is bounded by -1 to 1. So these share the similarity that as the logits, the pre-activation functions become larger and larger, extreme, then it can lead to gradients that are vanishing, which in this slide, it some to some of you might ask why this region is a vanishing gradient region where the y-axis, the f of x is 1. But we know that the gradients correspond to the slope. So we can, when we try to visualize the gradient with respect to this one is a sigmoid function, uh, we see that when the values are get higher and higher and lower, more toward the extreme values, the gradients become 0. And also for a sigmoid function, because the derivative of the sigmoid function is sigma times -1. Maybe I could write. So this indicates that the highest possible value would be 0.5, which becomes 0.25. This is the highest possible gradient, which corresponds to here. So naturally, the sigmoid function, as it gets multiplied within the chain rule, it will lead to vanishing gradients, which in order to surpass the vanishing gradient problem, the the um, the later activation functions such as a ReLU or leaky ReLU or ELU were introduced, which um, which will eventually covered, but not in this slide. Yeah. Oh, give me a second. I'm trying to erase this one. Okay. For this slide, the takeaway would be that even though we start with a values in a small range, which here it's um, sampling from a normal distribution, which would in the beginning it's a relatively smaller value. But as it goes through hundreds of matrix multiplication, the values become very big, which this would is a demonstration of why exploiting gradient problem might happen because it eh, because during the back propagation we're multiplying um, the for each layer we're multiplying the incoming gradients towards its current layers weight gradient of the with respect to the weight matrix or the um the x the input in order to pass it to the earlier layers. So there's many multiplication matrix multiplication involved, which as the as the multiplication compounds through multiple layers, it's very easy to lead to the this exploiting gradients, which could uh, which could later lead to instability in the training. So for these problems, all the previously discussed batch normalization or other techniques were devised. So I guess it would have been better to introduce this slide before those, but these are the motivation for the techniques that we went over, such as batch normalization. Okay. Um, about that, I'm having a difficulty. Right. So one another way to uh, overcome such vanishing gradient or exploiting gradient problem is to initialize the weights in a clever way. So because if we initialize the weights carelessly, then the training could uh, go wrong right away. Or one other example is that if we initialize all the weights as zero, all zero, or all constant, then each of the weights would be learning the same thing from the input. So there will be we will end up having basically duplicates of workers doing the same thing, which is redundant. So that is one of the reasons why we never set the weights as constants across each layer, so that we can give some variation in their starting point so that they can explore and learn different things. So if we do not initialize as constant, the first intuitive way, first naive way would be to random initialize. So, and usually this is typically done as uniform distribution, but this random initialization can also lead to um, I think there's one. Right. Okay. So yes. First of all, actually in 445 there will be uh, the representatives from the Blossom AI, so that they can go over your the AI platform that can be used for